Hey everyone, thanks for joining us. Welcome back to Build Squad stage here at ETHDenver. Next up, we have Namik. He's the Chief Strategy Officer at MegaETH. He's going to be talking about centralized block production for the execution layer. Welcome to the stage.
Thank you so much. Yo, what's up, guys? Packed house, as usual. Who here has heard about MegaETH? Put your hands up. Oh, fuck yes. Okay, this is going to be fun. I mean, people have like all kinds of pre-existing assumptions, but we can walk through a few of them. So, off the bat, like, what's the thesis, right? Which is no blockchain that's homogeneous, i.e. monolithic, i.e. the node does all of the tasks associated with the blockchain, will ever scale proportional to world compute, right? And what we see is just trade-off matrix. ETH, super decentralized, very lightweight, amazing. No one wants to use the L1. Solana is, a bit less decentralized, a lot more performant. And what you're seeing is a race to zero. A great example is like Fogo, which is an even more centralized layer one, and that's cool, they're really performant. And you start asking yourselves questions around why are L1s fundamentally have these constraints? And the answer is simple, it's consensus. Consensus fundamentally leads to performance degradation. The more decentralized you are, right, the more nodes participate in consensus, the longer physics kicks in and the less performant you can be. And that's not good. I think we have the thesis, which is smart contract systems have never actually found true PMF. That's why Bitcoin is doing much better than everyone else. And what we're seeing actually is that Solana is not very cheap either. I made this a very long time ago, this deck, but these days Solana costs a lot, almost as much as ETHL1. Now that's because there's like 2,000 real TPS on Sol, and like 5 on ETH. But TLDR, applications have not ever been able to really sit in the same block space comfortably. MegaETH solves this. We've built a very cool system where we effectively build specialized nodes, each doing specific tasks for the blockchain. And the end result is similar to what Vitalik wrote about back in 2021 in his article Endgame, where you see centralized block production, but maximally decentralized block validation. I'm happy to kind of walk through a lot of this with you guys. Or would you rather learn about like use cases and applications and all the reasons why this is cool? Should we do like some hands? Who wants me to go very deep into the tech? Okay, a couple. Awesome, so let's do it. So basically, we have a thesis, right, which is you have to get rid of consensus. You do this by effectively hyper-specializing for execution. What we do is we are, like, traditional blockchains are scenarios where every single node does all of the tasks, right? And this ends up creating a pretty annoying, let's see if I have this on this deck. Yeah, okay, I don't. So what it ends up doing is that you have this weird situation where if each node has the same hardware and software configurations and they do all the tasks associated with a blockchain, you need to make trade-offs, right? If you want to have a blockchain that's really, really good for decentralization, i.e. validation, that means it's going to be super lightweight, right? Well, that sucks for sequencing and execution. You end up in a scenario where like trade-offs are always made, and it's kind of the name of the game. For us, new data entered the market in the form of fraud proofs and forced inclusions, forced exits. And that basically told us, hey, no matter what, if the sequencer is censoring you, you can force exit back down to L1. And we saw this a few weeks ago, or maybe a month ago, with the Sonium L2, when it started censoring user transactions that were breaking their IP rules, and they were able to go back down to L1. So we take this piece of data and we're like, cool, what is the most performance-first architecture we can build? And then we come down to the conclusion that we need to specialize each task for a particular node. So what we do is we build effectively a particular node that does all sequencing and execution, right? Imagine an unbelievably beefy node. Way, way, way more centralized and way beefier than Solana. One sequencer. We never decentralize it, we never introduce consensus, and we use all kinds of cool optimizations and techniques. So think like in-memory computing, JIT compiling, parallelization, the whole shebang. Now we have a really, really performant piece of the puzzle, and because our whole thesis here is that we're going to build specific nodes for each task, we now need to build new node architectures for everything else, right? So one example ends up being like, how do we approach validation? What does our prover network look like? If you have a super beefy sequencer that, let's say, costs $1,000 to run, does it now cost $1,000 to run the prover? Because if so, that doesn't sound too decentralized to me. What we do is we use a technique called status validation, where we have a subset of the provers, this provers read a subset of the sequencer's transactions. TLDR, we've optimized the entire execution engine for what we know to do really well. And we outsource what we don't do so well. So DA is a great example, right? The biggest bottleneck of existing L2s is there's a pretty strong DA bottleneck, right? So we use EigenDA. And obviously for consensus settlement, we don't want to do that. That's really difficult. So we just fully outsource that to ETHL1 with the new guarantees we have, right? Which is effectively the power of fraud proofs and forced exits. Yeah, so I kind of spoke a bit about this, but traditional blockchains, one node does all tasks. MegaETH is like, yo, let's break that up into many different nodes. Yeah, so what we see here is effectively the node and hardware trade-off landscape. It's kind of what I described before. Provers are very, very lightweight, right? And you want them to be lightweight. Why? Because you want them to be decentralized, meaning anyone can spin one up. Now, sequencers are going to be really beefy. And that's fine because for you to build a truly performant environment and performant engine, you need pretty high hardware requirements. And you see the entire range in this little visual. Why do we make these design choices? It's kind of what we discussed before, which is proofs and slashing is really important to effectively enable the sequencer to be following these rules. MegaETH will be a test net, and mainnet will be optimistic rollup day one, but we're working very closely with all of our very smart friends in ZK land. You see, we like to outsource stuff on basically doing proof validation with like a ZK system. We think the guaranteed rights of forced exits are very powerful. Freedom of choice and ability to rotate the sequencer. So naturally, you're probably sitting here saying, okay, cool. These guys have basically fully centralized block production, meaning like Namik is going to be running this beefy sequencer, and sure, my transactions can be forced down to L1 if he decides to censor me, but like, what is this? This doesn't sound like a really good long-term solution for a couple of reasons, right? So we are going to be hitting 100,000 transactions per second on mainnet. That's 10 gigas and 1 millisecond block times. That's really, really great for co-location, high-frequency traders, all of these individuals. How does this actually impact you when talking about end-to-end latency? So in the land of end-to-end latency, one of the biggest issues is going to be like your geographical location, right? Where you are compared to where the sequencer is. Right now, the MegaETH sequencer on testnet is in Texas. So we can probably enjoy 50 ms end-to-end latency. That's equivalent to you playing Minecraft and having seamless UI UX. Now, naturally, if you're sitting in Tokyo, that's not very fair. You kind of have a horrible outcome. So what ends up happening is we're going to be rotating the sequencer to follow economic activity across the world, right? So the sequencer will be following the sun. This is a novel technique which allows us to effectively capture major pools of economic activity, right? It's quite simple. If it's 11 p.m. in New York, I guarantee you, maybe a couple of us are buying shitcoins, but the vast majority of people are asleep, while a lot of people are awake in Tokyo, and they're doing relatively important stuff, right? So this is actually a system that mimics FX markets. And we effectively will be having 3 main geographic locations, Asia, Europe, and the US, and we'll have a set of rotating sequencers between these different locations. Yeah, and why is this good? Because now Namik is no longer, running the solo sequencer. There's never consensus in the system. At any one time, only one sequencer, but it's able to rotate both for better UI UX, better capital efficiency, and removing key man risk. I guess here's another visual of the system design. You kind of are able to tell to what extent we have kind of rebuilt some stuff, but more importantly, which nodes do which tasks, right? And here you can really see the idea of node specialization to its core. We really think it makes sense given the new design choices associated with like more heterogeneous systems for you to be able to offsource a lot of the tasks associated with like nodes traditionally. So yeah, I guess how do we do this? A couple things. First, we're EVM equivalent, which is pretty sick because a lot of people aren't. We rewrote a new state trie. We built our own database effectively, just-in-time compilation, efficient state sync, streaming EVM. This is really cool because it allows us to actually enable real-time applications and obviously parallel execution once we have really good single-threaded performance. Yeah, so this sounds all fun and all, but like you've fully centralized block production. That's kind of concerning. Is there going to be any unlock here? I hope so. Our thesis is that by effectively making these design choices, we're going to be able to enable a level of performance that we haven't really seen before in crypto. We'll be able to get Web 2 parity with crypto economics, with permissionless systems, and actually accelerate adoption of just genuinely novel applications. So let me show you guys some simulations from my co-founder. What's the situation? So how many blocks what's the block time on Solana these days? 450 ms? Can someone confirm yes or no? No one knows? Pablo, do you remember? Okay. Let's just do 1 second for now because a lot of people are like aiming for 1 second block times, right? Something like that. If it's an L1, there's no network propagation. That just means, communication to and from the sequencer. This is what it looks like when I do something on my laptop on a blockchain of 1 second block times, and how that's going to be represented on chain. The bunny is supposed to follow the rabbit, right? It's pretty fucking slow. That's like good, by the way. That's the goal. 1 second is the goal for a lot of teams, right? So I believe Base just announced something pretty cool called fast blocks. Did anyone see that today? There we go. Bullish. I think that was 250 ms. Okay, close enough. And because Base is a single sequencer, you have to deal with network propagation. So let's pick a random number, and we'll keep that for like all networks that have no consensus. Okay, guys? So let's be generous and say 50 ms, right? Let's pretend the sequencer is close to us. Okay, sure, but imagine if you were playing Minecraft, you'd be pretty pissed. Or imagine you were playing a MMO, imagine you were playing Call of Duty, like you would rage quit, right? Okay, so now let's look at MegaETH. For context, the MegaETH testnet will go live next week. We are sitting at 10 millisecond block times for the vast majority of transactions. Let's just do 15 because this is complicated. And we're sitting at 1.3 gigas. Oh, wow. That feels pretty smooth, in my opinion. But I am I don't know much, right? Small brain. So I think this is pretty cool. And our whole thesis has been like, cool, we've made some crazy design choices, but we better find insane apps that will enable, like, we'll find this unlock, right? So we started a program called, by the way, this is our Echo deck. So I'm a bit lazy, so this is not fully relevant, but we created a program in which we had a bunch of founders that are super cracked. We made big bets on them to build applications which are only possible in MegaETH. They all leveraged that unique technological unlock of 10 millisecond block times to build real-time apps. These numbers have changed in the past few months. We now have 17 ecosystem teams who have raised around 35 million, right? And until our recent NFT sale, the applications on MegaETH had raised more than the chain than ourselves, which I think is pretty cool. ETH did that, but I don't know anyone else, right? I don't know, pretty cool. Okay, cool, that's it on my end. I'll give you guys back a few minutes, but, I don't know why, I just disconnected the HDMI cable, so. But I'm pretty excited. We'll have testnet next week. And it's really cool. There'll be some interesting applications. If you're a builder and you want to test the chain, please come and see me because I will give you everything you need to test the chain. And it's exciting. The benchmarks are good. And I think like we've made, in my opinion, the most logical construction for a settlement layer like Ethereum. Ethereum maximally focused on being the most decentralized Turing-complete blockchain in the world. In my opinion, existing L2s chose to replicate Ethereum's design choices and design principles. We didn't do that. We said, okay, let's take this new data and let's solve for what ETH is weak on, which is performance. And we built the most logical execution engine by decoupling consensus from performance. And we're excited. I think it makes a lot of sense. And yeah, thank you so much for your time today, guys.